So we're at Module 5B, Advanced Statistical Techniques, which follows on to the previous sessions that we had regarding renewal. So we're now going to look at repairable systems analysis. And the specific parts that we're going to look at is we're going to introduce the subject, look at repairable systems theory, and then look at integrated failure data analysis, where we then integrate the renewal theory with repairable systems. In other words, we are going to specifically look at when do we use renewal and when do we use repairable systems theory. Introduction. We say that up to now we studied the use of failure data to optimize the maintenance strategy for components using renewal theory. So we specifically looked at components, we used renewal theory for that, and we optimized the strategy for components there. Now the main premise of that theory was that repair is perfect, leading to the as good as new condition. But at the system level, we often experience reliability degradation. From our past discussions, we know that our ROCOF, the rate of occurrence of failures, increases typically for systems, and thus the degradation. The reason for that is that when the system fails, we only repair it minimally, meaning that we only repair the defective parts that we need to replace. The system is thus repaired to the as bad as old condition, the same condition it was in just before the failure. In other words, if we talk about our car and we replace the tires of the car is not better after we replace the tires. The car can just go on as it went on before the thread became too shallow. The theory that we can use to model this situation, which we call reliability degradation, is called the repairable systems theory. Okay, so then we quickly look at the theory. We say that repairable systems theory uses regression to model the long-term life trend of a system. Each of the components of such a system can, of course, be modeled using renewal theory, as we discussed in the past. We normally model in repairable systems theory the ROCOF and not the MTTF, which we could also model, but it is convention to model the ROCOF. The modeling technique that we will be using is that of the non-homogeneous Poisson process, or NHPP, which we show in Appendix B. We have a whole few pages there on the NHPP models, and we will shortly be looking at it. Now, in systems modeling, the time are denoted by T, the long-term arrival times to failure, whereas we use the short-term time, T, the inter-arrival times, in the renewal theory. In other words, we say that we now use a capital T for long-term time or the arrival time to failures, whereas we use small letter t or the inter-arrival times in the renewal theory. And the row cough we denote by row t, where that specific t that we have there, which is a small little t, should be a capital T. Okay, we have two models, two NHPP models. The first NHPP model is row 1t. Again, that must be a capital T, which is upwards concave, and row 2t with a capital T there, which is convex. And that's equations B1 and in B5 in Appendix B. And they look roughly like this, an example of row 1t, and you can see that it is concaving upwards. And an example of row 2t, and you can see that it is a convex, it flattens towards the end. The estimation of the parameters of these two models is described on pages 422 and 423. And we will now be quickly looking at the two models and the functions that are inherent to the models, and also how we estimate the parameters of the models. Okay, so let's look at the repairable systems theory then. The repairable systems theory uses regression to model the long-term life trend of a system. Now, regression, for those that does not know the word, just means fitting a mathematical curve to a set of data. Each of the components of such a system can typically, of course, be modeled using renewal theory. And in the use of the regression, we model the row cough over the life of a system, and not the alternative mean time to failure, which would also have been a possibility, but it has become convention to model the row cough. The modeling technique that we will be using is that of the NHPP models, the non-homogeneous Poisson process models, which are described in Appendix B of the textbook. The time in the systems modeling are denoted by a capital T, the long-term arrival times to failure, whereas we use the short-term inter-arrival times to failure, which is a small t in the renewal theory. The row cough is denoted by row t, where that t should really be a capital T, of course. And here's the relationship. Yes, the relationship is described. In renewal theory, we worked with the inter-arrival times between failures. In other words, we worked from the installation of a component to its failure was T1. T2 was the installation of the next component up to its failure, and so forth. And now in the repairable systems theory, we make use of the arrival times to failure. That is the time from the time 0 up to the point that the failure occurred. So when we talk about T3, the arrival time T3, it is the sum of T1 plus T2 plus T3. The estimation of the parameters of these two functions is described on pages 422 and 423 of the textbook. The two functions look as follows. The first one, row 1t, equals e, the mathematical e, to the power alpha 0 plus alpha 1 t. The alpha 0 and alpha 1 are then the two parameters of the function, which we will look at how do we find them on the next slide. Row 2t equals lambda beta t to the power beta minus 1, where lambda and beta are then the two parameters of the function. Now for the first function, row 1t, the parameters are found as follows. We have two equations here. The first equation we use to find alpha 1, and in the second equation to find alpha 0. In the first equation, the right-hand side is equals to 0, and is thus a fixed number. And on the left-hand side, we then need to find the value of alpha 1, because all the other quantities here are known, one has to find the value of alpha 1 that would make the left-hand side of this equation very near to 0. It will never become exactly 0, it will just get nearer to 0, or as near to 0 as you can get. And then the moment that you have alpha 1, you just substitute that in the bottom equation and you calculate alpha 0 directly. So that's for the first form of the NHPP function. For the second form, we have the following equations. And here we have a direct calculation of beta directly from this equation. That is the number of minimal repair occasions. And we then calculate this and divide it in there and we get beta. The moment that we have beta, we take beta and we put it in here and we calculate lambda. Like in the case of renewal, there's a spreadsheet to be found on our website that can be downloaded there that can be used to find these values. And in the case of the first form of the equation, one can again make use of the goal find function, the goal seek function of Excel to find the value of alpha 1 in this equation. We now get to additional functions that we can derive from the basic forms of row 1t and row 2t. So in each case, for each of these two forms of the NHPP function, we can calculate the number or the expected number of failures in a certain interval using one equation. For a second equation, we can use to calculate the survival expectations in a certain interval, and the third one we can use to calculate the expected mean time to failure in a specific interval. Now, in all cases, we can also calculate absolute numbers, in other words, absolute values of the number of failures, absolute values of the survival function, and absolute values of the mean time to failure. That is, absolute values meaning that you calculate it from 0 to some time point t by substituting 0 for t1. So when you substitute 0 for t1, you will get the value from 0 to the value t2. And that's really all there is to it. The moment that you have your alpha 1, your alpha 0, you can calculate all these values either for an interval value from a certain value of t to a certain value of t, or for absolute values from 0 to a certain value of t. For the second form of the NHPP function, these are the equations. They're all to be found in Appendix B of the textbook. Let's look at cost modeling in NHPP models. It's described on pages 423 and 424 of the textbook. As opposed to the purpose of cost modeling in renewal models, where it was specifically meant to balance the cost of failure repair against the cost of prevention, in the case of NHPP models, the purpose is to determine the economical life of the system, as we saw in capital modeling and capital replacement modeling as well. And here we work from the Rokoff trend graph to which we fit an NHPP mathematical model. The cost of minimal repair CF, the cost of replacing the system CP. Unfortunately, the two symbols used is exactly the same as the symbols that we used in renewal, but that is a convention in literature. It can cause confusion, so one must make sure that you don't misunderstand it. In this case, the cost of minimal repair CF equals the total cost of repair of the system over its life divided by the number of occasions of minimal repair. So it represents the average cost of minimal repair of the system. The cost of replacing the system, CP, which is the capital cost incurred in replacing the system. Now we're going to look at an example cost graph after we have looked at the equations by which we can calculate the optimal replacement point of the system as follows. For the first version, NHPP1 of the NHPP model, we can calculate the value of T star. T star here is then the optimal life. We can calculate that from this equation. Now, CP and CF are two figures that we estimate from actual figures. Alpha 0, alpha 1 we found. So the right-hand side of this equation is again a fixed number. The left-hand side of this equation, of course, varies by changing T star. And again, we have to find the value of T star that makes the left-hand side equals the right-hand side. We can again make use of the goal-seek function of Excel to find this. The second version of the NHPP function is much simpler. You calculate T star directly from this equation. At this point in time, one can maybe ask, well, why do we have two versions of the NHPP function? The one, as we saw, is a concaving up function. The other one is a convex function. And really what we do is we fit the two functions and we see which one is the best fit, and we use that one for the specific system. We typically won't make use of the spreadsheet, which was already mentioned, but we would make use of mAnalyst, which easily does the fits, and you can easily then compare the quality of fits and then choose your model. Right, and there is the cost graph then. There's the cost graph. Very similar to what we found in the renewal. Of course, we're talking of something completely different here in the sense that we now talk of the balancing of capital cost against cost of minimal repair. This was done for a Caterpillar 789 180-ton truck working at the Syferfontein colliery of Sasol at Secunda. The rand figures was converted to Australian dollars because this was meant for a paper that was delivered at the ICOMS conference in Australia. The cumulative life to system replacement on the one axis, in other words, long-term life of this machine, and on this axis, money. And this shows clearly that around about 20,000 hours the machine should be replaced. That is, of course, if all the data can be verified, whether it's correct and so forth, because it's a critical decision that one takes. In this case, the best age of the system replacement was found to be 21,000 hours, 21,293 hours. And the minimum average operating cost of this life was 123 Australian dollars, which is that amount there per hour. And if we leave the system replacement to 30,000 hours, in other words, at that point there, then it would cost us on average 150 Australian dollars per hour, which is a 22% increase. In other words, this shows that if we go past the optimum point, we will very soon find that our average cost over the life of the machine, remember these figures that we talk about here are the average cost, minimum average operating cost over the life of the machine. If you replace it at 21,000 hours, then your average operating cost over the life from 0 to 21,000 hours would be 123 Australian dollars per hour. But if you keep it up to 30,000 hours, your average cost over life from 0 to 30,000 will be 150 Australian dollars per hour. And you can think how high the cost must become past 21,000 hours to add the extra $27 per hour to this first portion of the graph. So it's critical that one replace it around about 21,000 hours for this specific situation. Remember again that one cannot say, well, if the same machine would work in another mine with different ore and maybe in another country with different logistical factors, that you will get exactly the same figure. It is really very user specific, this. We're now quickly going to do an example feed pump data on M-Analyst. The example is that in Appendix D of the textbook, it is example number 5. So we're going to do that, and after that, we will go on with the session. Okay, so we've now done the demonstration on M-Analyst. So now we get to the topic of integrated failure data analysis, which means that we, at some point in time, we have to decide whether we use renewal theory or whether we use repairable systems theory. And it might sound very silly or very simple, because renewal theory certainly are for components and repairable systems theory are for systems, but it's not always as simple as that. The fact is that within systems we have subsystems, and the question then becomes, do a specific subsystem, does it behave like a system or does it behave like a component? So we find a whole spectrum in between systems and components that we have to make a plan with. And really what we're going to do is we're going to let the data speak for itself. The simple answer is that when you have reliability degradation, then you have a system. If you don't have reliability degradation, then you have a component. So one has to do a test in this process, and we're going to look at that. Integrated failure data analysis then. We say renewal theory gave us a tool to analyze data without reliability degradation, which is typical of components. You see, we say typical. That's maybe the key word, typical. A repairable systems theory gave us a tool to analyze data with reliability degradation, which is typical of systems. Again, typical of systems. So that's typical of components, that's typical of systems. That's not to say that we can't find a component, although that might be very rare, that behaves like a system, and that we can find a system that behaves like a component. For this type of data, we make use of renewal theory. For this type of data, we make use of repairable systems theory. So the question is then, when do we use what theory? We've really already answered this. We have to know when reliability degradation is present. And we say that a trend of a decreasing mean time to failure or an increasing row-off, in other words, we're going to work with a row-off, will show us that. And that is described in Appendix C. Now we make use of the Laplace trend test to decide when we have reliability degradation. It is documented on page 430. And this is the test that Laplace developed. This test was developed in 1773 and is still regarded today to be one of the best tests for trend in failure data situations. We say the standardized variate, which was what Laplace developed, has a normal distribution with a mean 0 and a variance of 1. Now, firstly, how do we calculate it for a data set? We take the sum of all the arrival times to failure. In other words, from T1 up to Tn minus 1, the one just before the last one, we just do not include the last one. We add all of them together, all the arrival times to failure, and we divide that by n minus 1, so we get the average of the first n minus 1 arrival times to failure. And think back to our little diagram where we explained how the arrival times relate to the inter-arrival times. So we take that and we subtract from that the half of the value of Tn, the last arrival time to failure. And then that we divide by Tn itself, the last arrival time to failure, multiplied by the square root, this to the power of half, which is the square root of 1 over 12 times n minus 1. So that's how we calculate it. So if we have a failure data set and we want to know what is the Laplace value, we calculate it like that. Now, how does it work? The Laplace strength test works as follows. We say here it has the standardized variate has a normal distribution. What does not stand here, what we don't say here, is that it has a normal distribution with a mean 0 and variance 1 for all possible data sets that are trendless. We talk about data with and data without trends. And we said that we would, with data with a trend, we will make use of repairable systems theory, and data without trends, we will make use of renewal theory. Because data with a trend, we said, displays reliability degradation. So what do we say now? This little picture was made up by Harry Asher in some of his articles and in the book by Asher and Feingold. You will see that the numbers in here are exactly the same. You will see that the numbers are just reordered in the three pictures. So if they represent failure data, of course these examples are a little exaggerated, specifically for the purpose to make it very, very clearly to be seen, the patterns. So when you look at the first one, you will see that the lives, the inter-arrival times between failures becomes larger and larger. Now that Asher and Feingold, or Asher, called a happy system with a smiling face. It's a happy system because your reliability of the system is busy improving. The periods between subsequent failures or between subsequent failures becomes longer and longer. The bottom one is exactly the opposite order, and this is a sad system. It's a sad system because the lives between subsequent failures becomes shorter and shorter. The middle one, there's no real pattern, and that is what is called a non-committal system. In other words, you do not have a pattern. And these are the cases, the non-committal cases is the case where we over the long term can draw roughly an horizontal line through all our failure data points on a Rokoff graph. And those are the cases for which we can apply renewal. The sad cases where we have reliability degradation are the cases for which we can apply repairable systems analysis. The top one, the happy system, where you have reliability growth, we do not really have a model for, because that's not a maintenance situation. It is typically a specific engineering type of project and reliability improvement project where you will find such a pattern. So we are more concerned with these two. So for this one we will apply renewal theory, for this one we will apply repairable systems theory. This is a normal distribution with average 0, mean value 0, and standard deviation of 1, which means that you will have values between -3 and +3, because the normal distribution basically exist between -3 and +3 times standard deviation. And standard deviation is 1 here, so between -3 and +3. So that is the function that we're talking of. Now what do we say? We say that if we take all the possible data sets in the world that are trendless, and we calculate L for each of them, and we then take all those L's and we fit a distribution, a normal distribution to them, this would be the distribution that we would find. So all trendless data sets will fit into this distribution. So how do we now use it? When we have a failure data set, we calculate the value L for it, and then based on this distribution, we decide whether it has a trend or whether it does not have a trend. Now, if you refer to page 248 of the textbook, you will see that for a normal distribution, that 68% of the area under this whole curve falls between -1 and +1. So this area here represents 68% of the area under the curve. What does that say? It says that in 68% of the cases, failure or not failure data sets without a trend will fall in this region here. In other words, between -1 and +1. You will also see there that in 95% of cases, it will fall between -2 and +2, meaning that we have about 12.5% of cases in each case here in those areas. So much less than you had here. And in the last instance, very near to 100% falls between -3 and +3, meaning that you have a very small little percentage falling in these areas here. So when we find data, when we calculate L, and we find a value between -1 and +1, then we conclude that the data is non-committal, and thus that we would apply a renewal to that data set. When on the other hand we find the L value between 2 and 3, we conclude that there is a small little probability, which is this small little percentage falling in this area here, of it being a non-committal data set, but you have a much larger possibility that it is a SAD data set. So you conclude that it's SAD and you make use of NHPP analysis. When it falls on this side between -2 and -3 with the same argumentation, you conclude it to be a happy system, which is not really a maintenance situation. If it falls between 1 and 2, then again you have a possibility, this is about 13 or 12.5%, you have a possibility that it is a non-committal data set, but you also have a possibility that it is a data set with trend. So we call that a gray area, and we say that we will either apply NHPP or renewal. We can decide which one we apply. My position on it is that the nearer you get to 2, the more happy I would be to use an NHPP approach. The nearer I get to 1, the more I would be happy to use a renewal approach. But statistically speaking, you can make out a case for using both of the techniques. One can even do both, get 2 answers, and make a decision based on that. Again, between -1 and -2, you're again in a gray area, but because we do not have models for the reliability growth situation, we can only make use of renewal in this area for analysis. So that then regarding the Laplace test. You have in the book, you have another little write-up on how you interpret these, and there that is. There's also a decision diagram there, which is a diagram by Asher and Feingold again. We take our failure data, or our inter-arrival times, in the original chronological order, in the order in which it occurred, and then we test for trend using the Laplace trend test. If we find a trend, then we opt for the repairable systems models, because we then conclude that we have reliability degradation. You will see that we can also make use of imperfect repair models, which we have not looked at. So we will make use of the NHPP models. If we do not have a trend, we fall right through to a renewal process, which is okay. But if you really want to be very stringent, then you would again still conclude that the inter-arrival times that we started with there are identical distributed, because that's what we found by doing the trend test. They are identically distributed, but they are not necessarily independent. And then you can test for dependence. Now, what do we mean by dependence? When we fit a new component into a hole where we took an old component out. Remember, we talk of a hole in which a component fits. And if that hole was damaged by the previous component, by the failure of that component, and we fit the new component, then we will find that the new life of the new component will be dependent on the life of the old component. Now, that's the dependence for which we test here. If we find dependence, then we must make use of a branching Poisson process model. If we do not have dependence, then we can conclude that the data is independent and identically distributed. In other words, independent and identically distributed. Independent and identically distributed, and we can make use of a renewal process. Now, the fault, the mistake that we make by not including this test is very small compared to the error that we would make if we use renewal theory to analyze data with a trend. So because of that, the most critical test that you have to do is the trend test. The dependence test is of secondary importance. And that's the end of the module. Thank you.